Right, Andy, would you like to join me on stage here so that we can move forward? It's my pleasure now to introduce our next speaker, who is well known to, I think, pretty well all of you here. That's Andy Reisinger. In fact, to welcome him back to this stage. Andy, as you know, is a member of the Bureau of the IPCC, the Intergovernmental Panel on Climate Change. He is a member of Ross's Climate Change Commission, and he's been a contributor to two major reports on climate change for the IPCC, and he's in particular been working on mitigation strategies for some time now. He was well qualified to do all of that because before those roles he was with the Ministry of the Environment in New Zealand. Welcome back, Andy. The other role you played was Deputy Director as the international linkages of the Centre, and you're going to talk to us, I think, about international science. So, Andy.
Tēnā koutou, tēnā koutou, tēnā koutou katoa, ngā mihi nui kia koutou. Thanks for having me. Thanks for the introduction, Steve. I've been asked to give a summary of the global state of knowledge on climate change and responses based on the IPCC most recent suite of assessment reports. What do I click to move the slides forward? Is that one? Right. Which is quite a challenging undertaking. So the IPCC over the last two years released 3 major reports covering the science of climate change, impacts, adaptation, vulnerability, and mitigation. Each of those reports is authored by more than 200 authors drawn from more than 60 countries that looked at tens of thousands of scientific publications and processed many tens of thousands review comments in writing. Each of those reports runs to more than 2,000 pages, including appendices. So I'm not saying this to brag, I'm just asking your forgiveness if my summary in the next 15 minutes is somewhat selective out of this wide range of information. There's a lot of bad news to get through, but I'm trying not to fall into doomism. There will be some good news, but I'm German by extraction, so you will get your good news at the end. One of the key findings from the science of climate change is that the scale of recent changes across the climate system as a whole and in individual aspects is unprecedented over many centuries to thousands of years. We're no longer seeing climate change just as a change in the global average temperature. It's manifesting in many different ways. Increasing number of heat waves, loss of snow cover, loss of glaciers, melting of the Greenland ice sheet, shifting of storm tracks, increasing ocean heat content, rising sea levels, ocean acidification. If we have intelligent descendants 1 million years from now, they will see this century in the geological record. Right? This is non-trivial. We also know what's causing it. It is unequivocal by now that human activities are causing climate change through the release of greenhouse gases, which is also leading to an increase in a number of extreme events. And just to illustrate this, the graph in front of you shows the global average surface temperature reconstructed from proxy records and measured over the last 150 years or so, over the last 2,000 years. You can see how unusual, what a pronounced spike the Earth is going through at the moment, and it shows no sign of stopping. The warming is unprecedented in at least the last 2,000 years, and the warming now is exceeding the last multi-century warm period for at least the last 100,000 years. And we do know what's causing it. There is sometimes, and you've seen this in the last few days, a kind of benign denial and neglect from some media commentators that say, yeah, I'm not denying that humans are contributing to climate change. Sure, we're accelerating the climate change that's always happening. Our best estimate for climate change that would be happening from natural causes only is the green line on the right, which is pretty much 0. Virtually all of the warming that we are seeing globally can be explained by human activities, predominantly through the release of greenhouse gas emissions. We're not contributing to climate change, we are causing it, unequivocally. We also know quite a bit about what is causing it. Greenhouse gas emissions from human activities are currently at the highest level in human history. We've seen pronounced increases over all major groups of greenhouse gases: carbon dioxide, methane, nitrous oxide, and fluorinated gases. The graph on the right-hand side, I mean, we love to have an argument in New Zealand about the right metric to measure and compare greenhouse gas emissions. The graph on the right-hand side shows the inferred contribution of individual gases since the Industrial Revolution to warming based on climate models, not using any greenhouse gas emission metric. That shows you that the dominant contribution to warming comes from carbon dioxide, mainly from fossil fuel emissions, also from deforestation, but methane is causing a significant additional contribution to current warming, with nitrous oxide and other gases causing a more minor contribution. And it may be of interest to this conference and the participants that the agri-food sector as a whole is estimated to contribute roughly 30% of total greenhouse gas emissions, therefore 30% roughly of the current warming. Climate change is already affecting every region on Earth in multiple ways, and the changes we experience will increase with every increment of further warming. And of course, if we want to understand that, we need to understand how much more the climate might change, keeping in mind that it is us driving climate changes this and the coming century. In the IPCC assessments, we usually do this by looking at a range of scenarios because we are very strongly forced to be not policy prescriptive. We can't tell the world what it should do. We can tell the world what it might do and what the consequences might be. So there's a number of scenarios used to drive climate models that assume different evolutions of global greenhouse gas emissions from human activities over the 21st century, ranging from very rapid mitigation actions that reaches net zero carbon dioxide emissions and significant reductions in other greenhouse gases, shown in those small plots, up to a relentless increase in all those greenhouse gas emissions if the world basically pretends that climate change isn't a thing and we love coal-fired power stations. The right-hand side shows the projected increase in global average temperature. Under every one of those scenarios, the world will be warmer throughout the 21st century than it is today. The best scenarios that we have with the most ambitious action would limit warming to just over 1.5 degrees and perhaps result in a small decline in temperature towards the end of the 21st century. Or slightly less ambitious action might limit it to 2 degrees, or temperatures will continue to increase throughout the 21st century and beyond. That's temperature, but there's a number of geological changes that will be irreversible even if temperatures do reverse through ambitious mitigation action. In particular, sea level rise. Under any of those scenarios, sea level will continue to increase for many centuries to come. So our actions still make a difference, but they make a difference how much sea level will continue to rise, not whether it will continue to rise. A warmer world will result in higher sea levels. And in particular, because the changes are irreversible, they're also long-lasting. So current projections out to the year 2300, when not us, but our descendants hopefully plan to still be around, even one of the best-case scenarios for greenhouse gas emissions results in sea level rise of between 1 and 3 meters. That's one of the best-case scenarios resulting from limiting warming to under 2 degrees. If we fail to do that, sea level rise will be way above that. And you can picture what that means for many of our neighbors in the Pacific Island. The minister stole lots of my best lines, so forgive me, I did not coordinate. We do know that the changes in extremes are disproportionately accelerating with average warming. That relates to the dynamics of how the atmosphere works. For example, 50-year heat waves are already almost 5 times more likely than there were at the beginning of the 20th century, and they will continue to become more likely as the temperature increases. The same goes for intensity and frequency of heavy rainfall events, and we've had our fair share of that in Aotearoa this year already. There's been some efforts to try and, heavy rainfall is one thing, but what's the overall risk of that? How important is it? How will we cope as a society? And the IPCC has, for several reports now, tried to distill at a very high aggregate level key risks into what's called burning ember diagrams that simply illustrate how risks increase with the amount of global average warming that the world might experience. So on the left-hand side, you see the different evolution of global average temperature under different scenarios. And this is from a chapter from Working Group 2 of IPCC on impacts, adaptation, and vulnerability of some key risks specifically for New Zealand. And just to give you the example, the loss of natural and human systems in low-lying coastal areas, mainly related to sea level rise, but also linked, of course, to river flooding, you can see is already noticeable now. That's the yellow range, and will become more severe at about 2 degrees of warming and very severe under 3 degrees of warming, but it depends how well we adapt to it. Other examples, and these are sort of new, more compound risks that we're beginning to grapple with and where the scientific literature is only beginning to engage with, cascading impacts on cities and settlements across Australia and New Zealand, and I again hate to pick up on the Minister's last point, the failure of institutions and governance systems to adequately manage climate change risk is the compound effect of multiple crises where we haven't recovered from the last one, where institutions are fragile, where social consensus about how we should share the burden of recovery is potentially fraying. And that is flagged as a really significant risk that is starting now, and it will increase further with the total amount of warming that the world will experience. Again, adaptation strategies, leadership, good policies can make a difference, but we have to take those risks seriously. It's not just the individual amount of rainfall that causes the damages, it's how we as a society respond to it. Another key finding from the IPCC reports is that there are increasing gaps in between adaptation actions taken and what is needed, and those gaps are largest for most vulnerable and low-income groups. That's a statement that the IPCC wrote with regard to the global picture. However, this is sadly perfectly true for New Zealand. The people most affected by the recent extreme events are those who have no insurance in the first place, who live in precarious living conditions, who live paycheck to paycheck or beneficiary payment to beneficiary payment, who are cut off from communications. We see this now. And just to divert a little bit, sort of speaking of the Hikuai River, which is shown on that map, for example, there's been some images making the round on Twitter, which I think are really useful to illustrate a couple of points about adaptation and our prospects there. So that's one bridge over the Hikuai River in Tairāwhiti. The previous one was under normal summer flows, and these are images taken just at the onset of Cyclone Gabrielle. And you can see how this vast riverbed is slowly filling up and filling up, right? One thing that is really important here is that climate change is a stress multiplier. Climate change of 1 degree makes rainfall in the very rough average about 7% higher. You could argue, well, that means that 93% of any storm event, any flood event is not to do with climate change. That's right. Add 7% to that river flow. You know what's going to happen. The stress multiplication is the real key thing that breaks things. And in fact, it has broken things. I think this particular bridge held, a fair few number of other bridges didn't, and cut off a large set of communities from access, from support. It also illustrates that a focus on purely engineered solutions to adapt to climate change increase the risk from catastrophic failure. We've seen this in the failure of the substation that cut off power supply to many tens of thousands of people. It's bridges, it's lifeline infrastructure that is not well adapted to the climate we're in right now and makes it really hard to upgrade incrementally to a changing climate. And so I guess the key point I'm trying to make, and that's an illustrative figure again from the chapter on Australasia from the IPCC report, is there's a whole range of adaptation options. And an example for coastal management, they range from protection, accommodation to retreat, and there's individual actions one can take. Any one of those is a plausible first step. Any combination of those is a plausible first step. But we have to keep in mind, as sea level continues to increase, some of those will reach their limits. We are meeting real adaptation limits now. As climate continues to change, more and more of those options run out of steam and are no longer viable as a protection mechanism. So as sea level continues to rise, we have to think about how do we progress, how do we transition from one adaptation strategy to a next one. That's called dynamic adaptive pathways. That relies not just on a clear-sighted view of the options at any given time, but a question about trigger points, good governance system, clear policies, and political leadership that allows communities to change from one strategy that is no longer serving them well to a longer-term strategy that can be adapted as we learn, as time goes on. And keep in mind, 0.5 meter sea level rise is the very best scenario we can have for the end of the 21st century. And sea level will continue to rise beyond that. And the 21st century only has 77 years more to go. Which is, of course, the key reason why mitigation, reducing emissions, is so important, because it keeps options open for adaptation. It is not to serve some higher global good, it's because it's essential to keep climate change impacts manageable through adaptation. However, we're running out of time to limit warming to 1.5 degrees, which would give us the best chance of managing the impact of climate change. And I just want to illustrate this. So the IPCC looked at where our current policy is heading in terms of greenhouse gas emissions. So the graph shows you projected global greenhouse gas emissions out to 2050 under current policies, and where do our current commitments lead us, and where would we have to go if we want to limit climate change to 1.5 or 2 degrees. So the orange graph is current global policies. When I say current, that's when the IPCC report closed the gates for literature it could consider in October 2021. The NDCs, the nationally determined contributions under the Paris Agreement, would result in a rather small reduction from those current policies. They've since been updated. They haven't changed the picture fundamentally. There's still a gap between our current policies and how to even meet our current commitments under the Paris Agreement, and New Zealand has its own story to tell in that regard. By contrast, a pathway that would limit global warming to 1.5 degrees would see massive and immediate reductions in global greenhouse gas emissions. And in fact, the gap is so large that limiting warming to 1.5 degrees is no longer feasible if all we do is meet our current commitments under the Paris Agreement, under the NDCs. Simply, we've lost the chance of limiting warming to 1.5 degrees without at least temporarily significantly overshooting it. We could say, well, maybe 1.5 degrees was always too ambitious. Sorry, coral reefs. Let's just limit warming to 2 degrees. That would still leave a significant gap, but the gap wouldn't be quite as large as it is for 1.5 degrees. We could, in theory, aim to limit warming to 2 degrees, even though we only do what our current pledges say for 2030, provided we then rapidly accelerate the reduction of greenhouse gas emissions at a rate that's faster than if we were aiming to reduce greenhouse gas emissions consistent with 1.5 degrees. And that's, of course, enormously challenging if we spend this decade further investing in emissions-intensive infrastructure and industries. So limiting warming to 2 degrees is not infeasible if we stick to current commitments for 2030, but it relies on incredibly challenging and also politically challenging acceleration after 2030. The simple message remains that if we want to limit warming to 1.5 or just likely below 2 degrees, it does involve reaching global net zero CO2 emissions by the 2050s for 1.5 degrees or by the 2070s for 2 degrees, along with deep reduction in other greenhouse gases. Now, some good news. There are signs of progress, and they're not to be sneered at. There have been significant declines in key technologies, especially in the energy sector, solar, wind, battery storage, which have resulted in a massively, rapidly increasing installed capacity. This is really important because it means that things are now happening even without government and pricing incentives dedicated at reducing greenhouse gas emissions. There's been increasing policy coverage. We now have more framework legislation, net zero targets. We're using policy packages rather than just our favorite Phillips #2 screwdriver to do climate policy, a wider coverage of pricing schemes. There have been sustained reductions in greenhouse gas emissions in more than 18 countries, while those countries experience sustained economic growth. All of this means climate policy works. It does have an impact if done well. It also means that business as usual is no longer more than 4 degrees of warming, as it was in, say, 2010. It's now only 3 degrees of warming. But it also means that climate policy works if applied well and consistently. However, we are starting from a low base. We apply policy narrowly, inconsistently, and with insufficient ambition or finance. But we have proof of concept, and that's partially what you are after in the research field for agricultural greenhouse gases as well. So let's not belittle that. There are mitigation options globally that would allow us to reduce greenhouse gas emissions to about half the levels by 2030 at cost of less than $100 per ton CO2 equivalent. That's a non-trivial cost, but it's also a non-trivial achievement. We have a wide range of options across all sectors that can collectively be applied. So I'll just leave it with a quote from the co-chair of Working Group 3 of IPCC, Professor Jim Skee. Quite simply, we know what to do. We know how to do it. It is up to us now. Nō reira, tēnā koutou, tēnā koutou, tēnā koutou katoa.
Thanks, Andy. Stay. Oh, am I on? Yep. Thanks, Andy. Stay right where you are. I was thinking before your last slides there that if you came to this meeting feeling depressed, you would probably go home feeling suicidal. But there was a little cheer up at the end there. You put me in mind of Sir Bob May, outstanding Australian scientist who introduced us to chaos theory about 50 years ago, which is that before you see a very large change in a macro state of the environment, you are faced with increasingly erratic small changes, and they get worse and worse until suddenly, bang, you're in a new environment. And control theory also tells us that the longer you wait to try to correct that, the worse it gets and the more expensive it gets. And I think we're seeing examples of both those theories in action right now. So are there any questions to Andy? My one, I hope, to the administrators of the conference, I hope we can get your slides later. Sinead.
I tried out the app, but it obviously didn't work. Andy, a lot of confusion in New Zealand around the use of the GWP star metric. Can you comment on the assessment that the IPCC made on that metric? Because we hear sort of confounding things out there in the media around this metric. I'm sure you'll love that question.
I mean, ideally this would need a separate talk and slides, but that's just what I love doing. So obviously it matters how we compare different greenhouse gases, in part because many of the targets that companies set, that countries set, are expressed in CO2 equivalent with not much appetite to go ferreting through which gas is which. So there's a strong, a strong desire to do that, but there's also good reasons not to do it. So the IPCC has looked at, in its different working groups, at the physical science basis of different metrics and how could you compare emissions of different gases, in particular short-lived gases like methane that don't hang around for very long, but the warming effect lingers quite a bit longer than the emission itself, and other gases like carbon dioxide, which hang around for a very long time. And of course, any comparison, these two gases are different. Any comparison has to make some judgments about how do you compare them. It's a bit like if you compare apples and oranges, do you compare them by the sugar content, by the retail value, by how long they last on the shelf, or by the health benefits? You've got to tell me what matters to you, and then I can tell you what the best metric is to compare them. And so the IPCC has looked at GWP star is a new metric that compares not just an individual emission of methane with an individual emission of carbon dioxide, but rather looking at what happens if I keep emitting methane and how does that compare with an individual emission of carbon dioxide. It turns out that GWP star is very good at predicting the temperature change that would happen if I keep emitting methane. But the IPCC assessment also looked at what do you actually need to make policy decisions. For policy, you generally need to know how much warming would I avoid if I avoid this emission of methane. And GWP star, in the way that's been applied so far in the literature, it doesn't quite answer that question. It answers a question about how much does temperature change further. But what we know is that every ton of methane we emit makes the world warmer than it would have been otherwise. And for quite some time, so a ton of methane that we emit today makes the world warmer even 200 years from now than a ton of carbon dioxide that we emit today. So every ton of methane we avoid contributes to avoiding climate change. So there's different metrics that answer different questions, whether you want to look at how much damage does a ton of methane emitted today actually cause, and how does that compare to the damage that emitting a ton of carbon dioxide causes, or am I concerned about am I making the world even warmer than it is today? But it does raise the question, to what extent does making the world even warmer than today constitute an appropriate level of ambition? And it comes back to, what are we trying to achieve? And what are we trying to achieve is not something that the IPCC answers. It gives you tools to answer different questions, and it's very much reflecting on us, on everybody. What are we trying to achieve? Am I trying to minimize the damages that my actions today cause for generations to come? Or am I trying to limit the additional warming that my actions cause compared to the warming that my current actions are causing already? These are different questions, and the IPCC offers different tools to answer that.
Thank you, Andy. And that question is of immediate interest to pretty well everybody in the room, what we do about methane, obviously. There's a talk, you've got a microphone up the back, good. There's a speaker right up the back there, I think, who had your hand up. Did you?
Andy. Just building on that question, you showed a very pertinent graph with the warming that came from CO2 and the warming that came from methane. Now, obviously, a lot of that methane, if it's from a New Zealand perspective, is agriculturally based, as we know. What's the split in that methane on a global level? So from that plot that you showed, how much of that is fossil fuel origin and how much of that is agricultural?
It's roughly half is from fossil fuels, about 30-odd% is from agriculture, and the rest is sort of from waste from human activities. Maybe also worth pointing out that, the difference between fossil methane and biogenic methane, most of the warming that methane causes happens because methane is methane. There's some additional warming that fossil methane causes because it decays into carbon dioxide when it decays in the atmosphere. But if I look at the warming caused by emitting 1 ton of methane today, over the next 100 years, in aggregate, the fossil component only adds about 10%. 90% of the warming from a ton of methane emit today comes from methane being methane, regardless of whether it's biogenic or fossil. So it is worthwhile differentiating, and greenhouse gas emission inventories do differentiate that, but it doesn't mean that somehow fossil methane is fundamentally more problematic than biogenic methane.
Look, I agree with you, Andy, but you also did showed what food production contribution was. And often in the media, there's an extrapolation between that methane and the contribution from food. And of course, the contribution from food involves a lot of CO2 emissions as well. And then that extrapolation goes back to obviously sometimes ruminant production of methane. So no doubt we've got a big issue to solve, but some of the communication can be problematic and take, if you want, our eye off the ball of having that dual target of both fossil and agricultural methane. Thank you.
Thanks. Andy, do you have a last comment on that?
No, I'll let that stand as a comment on its own.
Okay. You were hiding in the shadows up there, but I'd recognize that voice anywhere as Jeremy Hills from Fonterra. Are there any other questions? No? Okay. Well, Andy, from my point of view, it's really nice to see you back on this stage. I'm, for one, very grateful that you're still continuing very active work in this field, and I hope we see much more coming out of you in the future. So thank you very much for your talk.
Thank you.